the system first.
哦，这个就聊起来了。手机 GPA 多少？
你有没有4.2？
As I mentioned last time, there's going to be a quiz next week, right? In the first week, you are going to have a quiz in the first hour, so you have to be on time. Don't be late, otherwise you're not going to have enough time for your test. So it takes 1 hour also. And after finish it, please come back for the lecture class, all right? We still have 2 hours for the lecture. It's going to be a real test and closed book, covering the material from the first week and until today's material, including the video file on YouTube on the chip manufacturer. Right? Let's continue the discussion of basic circuit. Okay, last week we mentioned that given a complementary CMOS logic gate, this is basic structure. There's a product network with PMOS transistor. There's a product network with NMOS transistor. The reason why we call that pull up or pull down is when it's on, you try to pull the output signal up to VDD. We said pull down network meaning it tries to pull down the output toward ground level, 0 volt. Okay? And typically, either pull down network is on and pull down network is off, or pull down network is on and pull up network is off, such that you're going to get a 1 or 0 in the output, given a specific input. However, it could be possible that the output is floating. Z, the symbol is Z, meaning there's no any signal, not 0, not 1, no signal, no voltage at all. Right? That's floating when both are off. When both are off, no connection to any power source. So there's no signal. And the other one is both are on. When product is on and product is on, we call that it should not happen at all. There must be something wrong with the circuit design. Because when both are on, VDD and ground are competing with each other, trying to pull up, pull down. So it's going to be some voltage level in between. You're not able to recognize either 1 or 0. There must be something wrong with the design of the circuit. So that's typically a static CMOS gate design. And we give some example. But we also mentioned that, so you can view each NMOS transistor or PMOS transistor as switches. Okay, and we mentioned a lot of time how you connect NMOS transistor in serial and in parallel. It will give you the specific result. In serial, both have to be on, then the whole network is on, the whole pack is on. In parallel, either one is on, then the whole network is on, the whole pack is on. So we give an example like this. It's a Boolean function at the output A and B or C bar. Typically, a static CMOS gate is a negative Boolean function. Negative is a bar over there. Okay. Why is that? Why is a bar on top? Because product level try to pull down the output signal toward 0. So when it's on, you get 0 at the output, right? This corresponds to the network of the product network. A and B, so A and B in serial. And correspond to serial, or correspond to parallel. So after you connect A and B in serial, disconnect with this transistor in parallel. And that will give you the Boolean function like that. And in port-up network, just complement. When A and B in serial, then A and B should be parallel. When AB and C in parallel, AB and C will be in serial. And that is the correct organization, correct structure for that Boolean function. Right? We call that a rule of conduction complement. When you are in here, serial, this must be in parallel. Parallel must be serial. Okay? Product network is a complement of product network. So, given a compound gate, another example, A and B or C and D, bar. So how do you divide the circuit? Well, it's easy. A dot B, so must be in serial. C dot D must be in serial. And AB and CD all together must be in parallel like that, right? And that's going to be your product network, the N network, MOS network in the bottom, right? Using MOS transistor. In product network, AB here in serial, then here in parallel, PMOS transistor. CD in serial, CD in parallel. And these two must be serial because this is two is in parallel. So that's the resulting circuit for that Boolean function. Giving you that Boolean function like that. And another example last week, given this Boolean function, A or B or C, the whole term dot and D, again, following the rule, A, B, C all together, so must be parallel connection, right? And D, so must be serial, right? This one and this one is serial. So complement connection, complement ABC in parallel, then ABC here in PMOS in serial. With D in serial, then here with D in parallel. So that's the eventual the circuit for that Boolean function. We also mentioned that for the actual example, given this Boolean function, A and B and C and D and E and F, but although it's doable, you can again divide the circuit for this Boolean function, but we mentioned that it's not a good design. Why is that? Because we prefer logic gate should not have too many input. How many? Typically should not be over 4. Typically. When you have 4 input, over 4, like 5, 6, 7, 8 input, then that gate is going to be very, very slow. The more input, the slower the circuit. Okay. So then what do you do? You try to decompose, not single stage large gate, but you decompose it into 2 levels. Here, 2 NAND gate, and then 1 OR gate. That's going to give you the same Boolean function, but that circuit is going to be faster than this circuit. Yes?
I have for this, there's have a rule for the breakdown from in the image and the
Yeah?
yeah, have a rule for breakdown. We can give 2 and 4 breakdown. If you understand what I mean.
Anybody can
We have 6 inputs.
Right, 6 inputs.
Instead, we need rule to divide in 3 input.
Okay. You mean like
Yeah, 4 or 2. Like
even more stages?
Yeah.
Okay. In this case, probably the no. because when you decompose it into two stages, the input reduced from 6 to either 3 or 2. That should be good enough. Let's say within 4 input, that should be fine.
Okay.
Over 4 input, try to decompose it into more stages. That clear?
So we
Typically 4 is the threshold.
can do here 4 input and 2 input also. Just like
4 input and 2 input. You mean 4 input and 2 input?
Yeah.
Is it better or is it worse? What do you think? It's worse because 4 input, this guy is going to be slow. Right? And furthermore, even though it's faster, but there's 2 levels. These 2 are in the same position, in the same state. And this guy is slower than this one. That's going to be your closest path, meaning that's going to be your longest delay. That determines your circuit speed. When we talk about circuit speed, we also mention worst case, right? Not best case. So that determines your circuit delay. Then yet, good question. Should be 3, no 4, 2, because then it's going to be slower. Any other question? Okay, and by the way, there's a NAND gate. Why is not OR gate? Because every AND gate. Why NAND gate, not AND gate? Because every AND gate is built from NAND gate, cascaded with the inverter. So that's the same thing. And by Boolean function, this is all together. Or right, that's correct. Yeah. All right. Any other question? At the end of the last class, we talk about signal strength. What does signal strength mean? It means that how strong, how close to the ideal voltage level for that signal, either 0 or 1. How close it approximates ideal voltage source. With 0 signal, how close to 0 volt? With 1, how close to the VDD? For example, 2 volt, 3 volt. And we also mentioned that on a chip, VDD and ground, where are the strongest 1 and 0? No other signal can be stronger than these 2. They provide the strongest signal. Actually, in real chip design, this is the chip. The VDD coming. Also, the ground coming. These 2 signals will be distributed everywhere on the chip. So there are many gates. Each gate connects with VDD and ground. So you can see that the VDD will connect many logic gates. Ground will connect many logic gates. They are connected together. So these 2 have to be very strong. So strong that the wire length, the wire width, is wire. It's metal. You remember the metal layer? When we talk about transistor for the chip manufacturing, right? The metal layer, the wire, for VDD and ground, they will be very wide. Not just 4 lambda, 5 lambda, 6 lambda, no. They are going to be very wide. Just like a tree, the trunk has to be very strong, very loud, very big to support many branches and leaves. Okay? in memory， 我们说一个晶片上面的 VDD 跟 ground 是电源供应，它将会在晶片上面贯穿所有需要它的电路、它的逻辑闸都需要 VDD 跟 ground， 而且它的这个导线会比里面一些连接导线来得更粗、更宽，不会只有比如说 minimum with 4 lambda，no，much wider than 4 lambda because they need a lot of current going through， 他们需要大量的电流经过 VDD， 因为它要供应一大堆逻辑闸，都需要 VDD 跟 ground。Alright， such that they can support enough current going through every gate on the chip. Alright, and so one thing important, MO transistor has strong zero, meaning this MO transistor acts like a switch. When gate terminal is 1, we mentioned that it is going to be on, right? The switch is on. So zero signal coming from here, you get zero signal on the right hand side. One signal coming from here, on the right hand side is going to be signal 1 again, because these switches are on. However, for MO transistor, it will pass strong 0, but it cannot get strong 1 on the right hand side, because MO transistor is good at transmitting signal 0, not signal 1. You're getting weak 1. What do I mean by weak 1? If pulse pipe is 2 volt, you're going to get not enough, not 2 volt, maybe 1.8, 1.7, something like that, which means that it's a weak signal. Well, although it's a weak signal, we can still recognize it's a 1, but you are not going to be able to connect too many fan out. If this signal will connect like 3 gate or 4 gate, probably should be fine. But you connect like 10, 20, 30 gate input, you're going to get trouble because signal too weak. They cannot, it's not going to drop so many gate input because the loading too high. Right? Meaning, given the same time span, time period, it should go up to 1. But it's not because the loading too high, it's going to be climbing very slow. So not between signal 1, maybe in between 0 and 1, just middle way, then time terminate, time is up. You are not getting signal 1, the real 1, because the loading too high. Look at it. When signal 1 is weak, you might use it to drive the weak 1. The mini fan out, for example, something like that. For weak signal, if fan, we call that fan out. Fan out is not much, should be fine. But if the signal is weak, and we are driving a lot of fan out, like 20, 30, probably is not strong enough to drive so many gates correctly, because even limited amount of time, you will not go up to enough high voltage such that it will give you signal 1. Is that clear? That's why signal strong or weak, we are concerned about that. On the other hand, for PMOS transistor, it's good at passing strong 1 instead, but degraded or weak 0, like this. You connect, it's on, source is 0, you're going to get weak 0. Again, it cannot drive too many gates. And by the way, for NMOS transistor or PMOS transistor, it's symmetrical. You can see that they are symmetrical. Signal can come from left and going out on the right. And also it can come in from the right and going out to the left. Either way is fine, can work. That depends on where the signal source. Signal source determines what direction for NMOS transistor and PMOS transistor in this case. And that's also why NMOS transistor is good for pull down network, and PMOS transistor are good for pull up network. Pull up trying to conduct signal 1. Pull down trying to conduct signal 0, right? Any question? So that's it. NMOS transistor, PMOS transistor are switches, can be used as switches. And when gate 1, gate 0, these are on for the switch. But you have to be remembering that when NMOS transistor is on, it's not going to transmit strong signal 1. For PMOS transistor, it's not going to transmit strong 0, but degrade 0. Okay, try to remember that. 把它背下来。And now we are trying to build some circuit based on the NMOS transistor and PMOS transistor. These are the switches. The first one is transmission gate. Patch transistor produce degraded output, so our transmission gate can pass both 0 and 1 way. And this is the circuit. Can you see what the connection here? The NMOS transistor, the PMOS transistor connected in parallel, right? This end together, this end together. So when G is gate, when gate is 1, so gate bar will be 0. G is 1 and GB meaning bar, right? It should be 0. Both are applied to this gate. Then what? Then this transmission gate is a switch. It's on. And its input either from here or from here. 0, 1 will give you the same 0, 1 in output. They're going to get it. And also, the point is that either A is 0 or 1, you're getting good 0 and 1 at B. Why is that? Because if A is 0, the signal comes from there. A is 0, then 1. But we say NMOS transistor can conduct good 0 in output, right? Go this way. When the input is 1, we go this path. The PMOS transistor will give you good signal 1. Although the other branch is weak 1, but when you connect them in parallel together, weak connected with strong becoming strong. Okay. 所以连并联的时候，一条讯号是弱，一条讯号强，合在一起还是强的。它就一条是强，它就是强的。Alright? So here, 0, 1, both are strong. But I have to remind you that when we say for transmission gate, this strong 0 is strong 1, not as strong as the inverter or NAND gate output. No. NAND gate or inverter, they are still stronger than these two signals. Meaning, this is a NMOS transistor, PMOS transistor inverter. is a circuit for the inverter, the input and output, VDD, ground. Then input 0, you get 1 at the output. Input 1, you get 0 at the output. But this signal 1 or 0 at the output is stronger than these two signals. Why is that? Because for this output 1 or 0, it's going to go through PMOS transistor when it's on. The source is power supply VDD. When it's on, it's off. The source is ground. Again, very strong, very strong 0 signal. So 1 and 0, either one should be very strong. But for this transmission gate, the voltage source is not VDD or ground. Although you're getting good, but not as good as this kind of steady CMOS gate output. And these are the alternative symbol. They are the same, just different way to draw the symbol on the paper. 可是不能画，但是都一样，是纯粹给，就当这个数据对。你可以去。Alright. Another circuit, we call that tri-state buffer, tri-state switch. Tri-buffer or tri-switch, the same thing. The symbol looks like this. Triangle, and there's an enable control signal. A the input, Y the output. Or you can draw like this. Enable here, and enable bar, bubble here. These are the same, just different way to draw the symbol. What the function here? It's just like switch again. But tri-state buffer, tri-state switch produces Z when not enabled. When enabled, it's 1. Let's look at here. An input 0 or 1. You're getting 0 or 1 at the output. Simply transmit through the gate. However, when enable is 0, no matter input 0, 1, you're getting Z, meaning no signal. So simply put, we turn down the gate, turn down the switch. 把开关关掉，不给它任何讯号来源。When enable 0, you're turning off. So Y output has no signal at all. Not 0, not 1, but no signal. Only when enable is 1, you're getting 0 or 1, depending on your input. But what's the difference from this one and transmission gate? They look like the same. In terms of function, they're similar circuit. Okay, here is the difference. Transmission gate acts as tri-state buffer, right? The function is tri-state buffer. And it only means two transistors, very small. Okay, very small circuit, but non-restoring. The key point is non-restoring. Not only that, Y output is not very strong, it's strong, but not very strong signal. But also, noise on A is going to pass on to Y. What I mean? We enable here, then it's on, it can go through. However, you look at the waveform. Typically, the waveform is not going like this. No, it's ideal. Voltage 0, ideal voltage 1, and 90 degrees, very steep. However, if you look at the oscilloscope, the equipment, 如果你看示波器 they are more like this. There are some fluctuation. Okay, this is real waveform, and also it's going to be noise. Noise can impact your signal. Noise appear everywhere. Okay, in the air, anywhere. So the signal is not going to be look like this, but it's going to look like this. If this your input is A, what is Y? Is A. So what is Y? It's going to be Y. It will look like this. Again. Maybe even more noise. Okay, this is not accurate, but Y would be look like that. A little bit later, there's a delay. There's going to be a delay. Something like that. Output will be a little bit later because of the delay, the gate delay. And we don't like that. Because in the transmission gate here, and another transmission gate here, you connect two transmission gates cascading. After one transmission gate, you introduce some noise. After one transmission gate, you introduce more noise. Although you connect several transmission gates in series, but the output at the end is going to very bad signal. A lot of noise. Also, voltage drop, not very strong. However, for the gate circuit, something like okay, inverter, something like that. Okay. Input A, output Y. For the inverter here, the input looks like this. Y output. What would Y output look like? Can you tell me? Invert, right? 0 should be 1, and then 1 should be 0. However, the signal is going to be clean. It's going to be clean. Although some delay again introduced, but the signal is clean, meaning this noise is going to be filtered out. Why is that? Why this gate can filter out the noise? This is what non-restoring means. This is non-restoring. It's restoring. Restore to good level. Restore to good clean signal. And why is that? Okay. For this circuit, just imagine that. Given some noise in the input, okay, some fluctuation, but the noise is not large enough such that you are getting wrong recognition, right? We can still recognize, yeah, you are them, but you are still 0, you are still 1. We know that the gate can recognize that. And when it recognizes either 0 or 1, either PMOS transistor is on, is off, or this off is on. You are getting good signal from 0 and 1. That's clean, 0 and 1. Let me repeat it mentally. 我们刚才讲的意思是说，一个像这样的 inverter or any other gate， 任何的逻辑闸 as long as it's typical CMOS gate connected to VDD, connected to ground, pull down, you are getting clean signal for 0 or 1. 你的 input 虽然有杂讯，但你不管杂讯再怎么样， 除非它太大，否则你仍然可以认识辨别它是0，它是1，对吧？你可以辨别。那既然是0或1，一定是只有一个通，一个不通，一个不通，一个通的其中一种情形，你将得到一个非常干净、没有杂讯的1或0，因为它知道它是0或1，它直接连接transmission，那个 transistor， 它会给你的讯号是漂亮的、干净的讯号，把杂讯给滤掉。This kind of CMOS transmission gate, a CMOS logic gate, will filter out, will remove the noise at the input. So you can see the trade-off. For this kind of circuit, using transmission gate or PET transistor, small, very small, and also fast. For the other CMOS stated logic gate, it consumes more transistor, it consumes more chip area, but it's going to give you very clean signal, a very strong signal. Okay? There's a comparison between these two kind of design style. 这是一个取舍，就是有优点有缺点。transmission gate 非常小，面积很小，它速度够快，但是呢，你得到的讯号是一个比较稍弱一点点，而且会杂讯是会累积的，会连接越多。When you connect more transmission gate, you're getting more and more noise. So actually, in some unit design, we like small chip area. We also like clean signal. Then what can you do? You can try to connect, example, something like 3 transmission gate, and then you try to give inverter, or maybe 2 inverters for the output. They will give you small chip area, and that will give you the output good signal, both strong and also clean in the output. So just some kind of combination. 就利用这种方式，你可以前面可以用transmission gate来做，可以降低面积。但最后的话呢，再加不能连接太多，连接太多它有可能讯号会太差到会变成错误。最后再给它加一个，比如2个 inverter， 那你又恢复到正常，可以给你干净的讯号的输出讯号。那这样可以兼具两者之长。So this is a static CMOS gate, but we again design a tri-state, some kind of tri-state switch, but it's an inverter, tri-state inverter. Tri-state inverter produces restore output. This is good. We like that. We like restore output. Not like transmission gate. It's a non-restoring. But the structure, the organization, violate conduction complement rule. So we could have Z output. This is what we want. Look at this circuit. What do you think? What's the operation? 2 PMOS transistor and 2 MOS transistor. A input connected, P, 1P and 1N. Enable connect here, enable bar connect to here, PMOS transistor. Then 1. When enable is 0 or 1, right? Enable is 1. 1 here, 0 here. So it's on. It's also on, right? And then what? Just treat this pad is a wire, simply a wire. And this circuit is an inverter, right? 当你今天有它导通的时候，那它就等于是等同于是就连接线而已。那它就是一个 inverter 电路吗 ？Inverter like this. However, when enable is 0, the one is 1. Then what? PMOS transistor is off. MOS transistor is off. What is floating? you're getting Z， 它就像被断绝任何连接，它变成绝缘体一样。这是它们连到任何东西，它被所有都被绝缘体给包覆着。Why you're not getting any 0 or 1, but simply floating like this. And the symbol do like this. Inverter, but there's an enable signal. Or enable bar. Either one is okay. We call that tri-state inverter. It looks like a tri-switch, but giving inverting output. Similar to tri-state switch, but it's giving you the negative, the inverted output. And let's say it's a restoring circuit. You're getting good and strong signal, clean and good signal. Alright, so let's move on, and we are trying to design a 2-to-1 multiplexer. You probably have already learned what is 2-to-1 multiplexer in digital logic design, right? That's a symbol here. D0, D1 are input, Y output. S is selection. That's the control signal. When S is 0, D0 is going through the multiplexer and appear in the output Y. When S is 1, then D1 will go through. So this truth table will give you the input-output relationship. When S, as I say, when S is 1, that will give you output just go through. Just go through. It's choosing this input or this input, right? That's 2-to-1 multiplexer. So how do we implement that? How do we design the circuit? 要怎么设计呢？ First of all, let's try to give the Boolean function. Okay, this is the Boolean function. Can you see that? Simply looking at the function, you should be able to tell this is a 2-to-1 multiplexer. Why? When S is 0, then what? When S is 0, 0 is equal to 1. You're getting D0, right? When S is 0, 0 and D1 getting 0, right? 0 and any signal, 0 or 1, you're getting 0. 1 and D0, you're getting D0. This is a basic Boolean function. 0 and anything, you're getting 0. 1 and anything, you're getting this one, right? So Y and D0, the output. On the other hand, if S is 1, S bar is 0, you're getting 1, you're getting D1. That's exactly the function of 2-to-1 multiplexer, right? So how many transistors are needed here? Well, that depends on your design. There are quite a few design alternatives. If just simply use the basic logic gate, inverter, AND gate, OR gate, then that's the circuit here, right? And if you implement each gate with a static CMOS gate, then you need 2 transistors, PMOS and MOS. 2 input NAND gate, 4 transistors. 2 NMOS, 2 PMOS. Inverter again, 2 transistors. OR gate, 4 transistors. Inverter, 2 transistors. So totally, that's quite a lot of transistors. That's going to be 20, right? Yeah, 20 transistors. But before that, why these two are equivalent? Like I said before, AND gate actually is built from NAND gate cascaded with inverter, right? There's no real AND gate for the CMOS logic gate. Eventually, we are implemented with NAND gate inverter. And the same thing for OR gate, again, steady CMOS gate is negative logic. You have to use NOR gate and then inverter. So that's from implementation point of view, you need so many logic gate. Is there any improvement? How to improve it? 有没有可能可以改善呢？We don't like that. There are too many transistors. Maybe just look at this circuit here. Can you come up with another design? It will give you the same function, but it's simpler. 有没有可能可以给一个电路的设计，它呢可以一样的功能，但是它不要花那么多 transistor. It can be built up with fewer transistors. Actually. How about this? Does it work? Are they equivalent? Or in terms of Boolean function? Is that correct? You see that? Let's put 2 bar here. It's going to be clear, right? And then apply this bar, distribute it toward the emitter. SD1 becomes SD1 bar, or become N, Morgan's law, right? And this bar apply to here, S bar become S. These will become this here. Yeah.
Yes.
Wait. Yes. I'm sorry, the connection is wrong. Yes? Here. Okay, then E0. Right. That's correct. I'm going to repeat it. This Boolean function, put 2 bar here. They cancel each other, right? And keep the top bar there. And this bar is going to be distributed inside. SD1 become SD1 bar, or become N. S1, S bar D0 become S bar D0 bar. These two are equivalent. So looking at this equation, this wave function, S1 and D, AND gate. S bar, D0, NAND gate, right? Two NAND gate. And then again, NAND gate. So these two are actually the same circuit, equivalent. Right? And how many transistors do you need here? You need 2, 4, 4, and 4. Only 14. So this implementation is going to be better than this implementation because it has fewer transistors. There's some improvement, right? All right, let's take a break.邱医师，中央昨天已经记了哈，然后台大我今天会记完。
哦，好。
那其他就再。
我今天有在把剩下的东西传。
OK，对，好，那
今天可以。
好 ，OK，
今天可以。
那你是这礼拜东西都会传完吗？
啊？
你是这礼拜这几件都会传完吗？还是会剩什么中央之类的？
这几天都会传完，什么意思？
就是推甄啊，是这礼拜就结束了。
今天中央结束，然后7号台大结束，
然后青椒。
然后青椒11号结束。
哦，所以会用到双10。对。
会用到双10吗？其实我根本不知道改什么，我都是。
所以你用完了。
我用完了，我都是差不多的东西放上去。因为我不知道怎么量身定做，你知道吗？我没有量身定做。
那你还是把重点送去放在考试吧。
我就是。
感觉是这样子。
我就是只有交大是那个，